NENOMATICA, where mathematics meets YouTube excellence. We will derive the closed form for the floor of 2x step by step using the standard rules for floors and fractional parts. First, let's show the example label and the problem statement in bold orange. Step 1. Use the definition of the floor and fractional part. Title the step. Then show the decomposition of x into its integer and fractional parts, and the bound on the fractional part. Step 2. Use the property that adding an integer inside a floor can be pulled out. Show the step title. Then expand the floor of a sum by decomposing both numbers into integer and fractional parts. Next, slide the integers out. Step 3. Use the cases for the sum of two fractional parts, which can only produce 0 or 1 when floored. Show the step title. Now show the two cases for the floor of x plus y. Step 4. Substitute y equal to x, so that the floor of 2x is the floor of x plus x. Show the step title. Then write the two cases explicitly, highlighting the doubled fractional part in orange. Step 5. Simplify the expressions and convert the conditions from the sum of fractional parts to a condition on 2 times the fractional part. Show the step title. First, combine the integer parts to get 2 times floor of x. Then write the cases in terms of 2 times the fractional part. Finally, isolate the fractional part to obtain the clean, standard piecewise form. Welcome! In this example, we will build an intuitive algorithm for floors and fractional parts, then derive rules for 3x and general nx, and finish with Legendre's formula for factorials. Step 1. We split any real x into its integer part and fractional part. We write x equals floor of x plus fractional x, with fractional x between 0 and 1. Step 2. Apply the floor to a sum x plus y plus c. First, write each as integer plus fractional. Then use the fact that integers move out of the floor unchanged. That leaves the floor of the sum of fractional parts as the only place where case analysis is needed. Step 3. Now, we consider the possible sizes of the sum of fractional parts. Because each fractional part is between 0 and 1, their sum lies between 0 and 3. Depending on whether the sum is below 1, between 1 and 2, or between 2 and 3, the floor adds 0, 1, or 2. Step 4. Apply this to the special case where x equals y equals z. Then we analyze the value of 3 times the fractional part of x. Dividing the ranges by 3 gives a clean rule in terms of the fractional part of x alone. Step 5. Generalize to any positive integer, n. The floor of nx equals n times floor x plus an integer k that depends on the fractional part of x. That k is the unique integer from 0 up to n minus 1, such that the fractional part of x lies between k over n and k plus 1 over n. Step 6. Legendre's formula gives the exponent of a prime p in n factorial. We sum the floors of n divided by powers of p, stopping when the term becomes 0. To wrap up, here are two compact formulas to remember. First, the general nx as a piecewise rule, or via n times floor x plus k. Second, Legendre's formula for v sub p of n factorial. In this example, we will find how many trailing zeros the number 1993 factorial has, following a clear 5-step method. Step 1. Understand the prime factorization formula, often called Legendre's formula. It says the exponent of a prime p in n factorial is the sum of the integer parts of n divided by powers of p. The brackets mean we take only the integer part, ignoring the decimals. Step 2. Identify the cause of trailing zeros. Trailing zeros come from factors of 10, and 10 equals 2 times 5. So the count of tens in the factorization tells us the number of trailing zeros. Step 3. Determine the limiting factor. In a factorial, there are always more factors of 2 than factors of 5. Therefore, the number of tens is limited by how many 5s we have. So we only need to count the power of 5 in 1993 factorial. Step 4. Compute the power of 5 in 1993 factorial using Legendre's formula. We sum the integer parts of 1993 divided by 5, 25, 125, and 625. The next power, 3,125, is already larger than 1993, so it contributes 0. Step 5. Final conclusion. The number of trailing zeros of 1993 factorial equals 495. That is the final answer. In this lesson, we will solve a classic factorial problem using the rules of bracket, also known as Legendre's formula. Our goal is to find the exponent of the prime 3 in 14 factorial. We will follow the exact 3-step algorithm. Set up the brackets, compute each bracket using the floor, and add the results. The formula says the exponent of a prime p in n factorial equals the sum of floors of n divided by powers of p. That is, the floor of n over p plus the floor of n over p squared plus the floor of n over p cubed, and so on until the powers exceed n. Step 1. Set up the brackets for n equals 14 and p equals 3. We write the floor of 14 over 3 plus the floor of 14 over 9 plus the floor of 14 over 27. The next power, 81, already exceeds 14, so we stop here. Step 2. Compute each bracket using the floor, which means take only the whole number part. For the first bracket, 14 divided by 3 is 4.66 repeating, so the floor is 4. For the second bracket, 14 divided by 9 is 1.55 repeating, so the floor is 1. For the third bracket, 14 divided by 27 is 0.51 repeating, so the floor is 0. Step 3. Add the results exactly as the algorithm shows. For plus 1 plus 0 equals 5. So the exponent of the prime 3 in 14 factorial is 5. Final answer. The exponent of the prime 3 in 14 factorial equals 5. We can write v sub 3 of 14 factorial equals 5. For intuition, let us also see why this makes sense. Among the numbers from 1 to 14, the multiples of 3 are 3, 6, 9, and 12. Each of those contributes at least one factor of 3, giving 4 factors. The number 9 contributes an extra factor because 9 equals 3 squared. So we have a total of 5 factors of 3, matching our bracket result. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.